So, hi everyone. So, as I introduced myself before, I'm Joshua Crittenden. Um, Currently working on Project 5 for the Superfund Research Center. And I presented 2 years ago. So, this is kind of an update on some of the progress that we made so far. But overall, we're really looking to identify and isolate PAH degrading fungi and bacteria in esturine-influenced creosote contaminated sediment. Yeah. So our project site. So we are working up in the Elizabeth River in Virginia. And so it's in the metro area near Portsmouth, in several other cities. There's been previous work done on different contaminated sites. In the image on the right, you can see the different levels of pH contamination occurring with Atlantic Woods Industries, as well as Republic Creosote site, which is something we're looking at specifically. So a little bit about creosote and pHs. So essentially, coal tar creosote was used as a historic preservative for wood. So if you think about telephone poles, railroad ties, anything where you really need to use wood for the environment, creosote was kind of used as a preservative to ensure that the wood doesn't decay or doesn't weather over time. And with creosote, it's largely comprised of PAHs, which we know are mutagenic, carcinogenic, and teratogenic. And they've been deemed as a legacy pollutant and have been found at 155 active Superfund sites for a couple of decades now. So when we talk about pH remediation today, oftentimes it focuses on physically removing the contaminants from the site. So this can be done through two different options. The first is through dredging. So dredging is we're bringing out machinery to the contaminants and actually physically digging them out. Will it be transported off-site to either be disposed of at a hazardous waste site or either be biologically treated somewhere else? Or through capping, which capping essentially creates a barrier which helps to immobilize the pHs so that they're not continuing to spread across or they're not continuing to disperse. So both of these methods are very, very expensive, and oftentimes we're not able to, or oftentimes when we're looking at remediation strategies, the price is an inhibiting factor. So we're looking to bioremediation as a way to provide an alternative for these two. And when we're talking about bioremediation, oftentimes we focus on bacteria. However, we know that fungi have the ability to transform these legacy pollutants like PHs. And so, quick story. So when fungi was starting to be seen as a way to clean up pHs, they actually found it through fungi being able to grow on telephone poles. Like I said before, telephone poles were treated with creosote. However, throughout the South, there were still issues in which fungi was still growing on those telephone poles. So back in 1985, they were able to culture over 1,300 fungi from these telephone poles. It's showing that the creosote was being depleted. And a lot of that attention started to be placed on white rot fungi and Basidium mycetes and their ability to transform these compounds. So like I said before, bacteria is oftentimes used in these models. However, bacteria are not able to necessarily transform larger pHs. As you saw in the previous slide, pHs come in different rings. So oftentimes when we look at the 4 and 5 ring compounds, they're less bioavailable to the bacteria. However, with our strategy, we're looking to implement the fungi to help transform those 4 and 5 ring compounds through their extracellular enzymes that they produce, such as lactases. So previous work done in our lab, so we've actually worked at a Superfund site out in North Carolina near Kernersville, I believe. And we were able to kind of isolate fungi coming from the soil of a contaminated creosote site. So a lot of them came from a different phylum. So like I said before, the white rot fungi were Basidium mycetes. However, the fungi that was found from our lab at this site in North Carolina were from the ascomycetes. And so they were in the soil as opposed to basidiomycetes being on wood. So they were actually kind of seen as more promising candidates in the bioremediation scheme. And so this gave way to my project, in which we were looking more so for organisms in the soil to help promote the degradation of pHs. So on the bacteria side, again, previous work that was done, again, we were able to identify pH degrading bacteria up at our site in Virginia through different means such as DNA stable isotope probing and culture-based isolation. So in the image on the left, you see spray plates in which we were able to culture the plates with bacteria and basically spray pHs on them. And there you can see the zones of clearance occurring on those plates. So this kind of leads to really my project. So again, what we're really looking to do is developing a precision bioremediation framework that exploits the cross-kingdom interactions to initiate biodegradation of pHs. So all that to say is basically we're trying to use bacteria and fungi in their different mechanisms to, again, help transform the pHs in the environment. So like I said before, using both indigenous bacteria and fungi for transformation. Like I said, the fungi produce these enzymes that are able to transform the pHs into byproducts. We hope that these byproducts will then be available to bacteria. And looking to, again, do this through creating this joint fungal bacterial biofilm. So work so far. So again, I'll go through this quickly in the next couple of slides, but we're able to go through the contaminated sediment at our site in Virginia. We're able to isolate and find different fungi and test for their different abilities to produce different enzymes that might be of interest. From there, we're able to take these different fungal isolates and then incubate them in the presence of pHs to see whether or not they were able to transform the pHs into different compounds. And then from there, we are looking to see if we can upregulate these enzymes that these fungi are producing. So basically, how do we ensure that we can get these fungal isolates that we just found to make more enzymes to help speed up the process of degradation? And then again, looking to, again, re-incubate them and test them in the presence of pHs for further transformation capability. So this is just an image of kind of what we kind of did in terms of isolating the fungal isolates. So as you can see, there were different media used to kind of select for different isolates right there. From there, we're able to test and kind of see the enzymatic productions. So for this specific experiment that you're looking at in the image on the right, we were testing for lactases. So if an isolate was able to produce lactases, you would see a blue or green color change. So obviously with these isolates that you see in this image, they were positive for lactase production. So we were able to, after sequencing 160 isolates, we were able to choose 18. And these 18 isolates reflect both lactase producers and non-lactase producers, but we were able to kind of do more tests on them to kind of see what other enzymes they were able to produce. And so on the left, again, this was a tannase assay in which we were kind of looking to see whether or not fungi were able to break down tannins. On the right, you were able to kind of see a cellulose degradation. So again, whether or not these isolates were able to break down cellulose, again, because in the natural environment, cellulose is common in a lot of organic material. And from there, we went into initial round of pH incubations. I'm trying to speed through, sorry. And we were able to kind of get candidates that were of interest. So basically, we have about 5 candidates. So these were candidates that were pretty much in high potential, that we see them as really good candidates for moving forward with a joint fungal bacterial biofilm. And then these were kind of secondary candidates, which we do have of interest to kind of using going forward. Future work, so this is work that I've been doing for the last couple of months. It was looking at upregulating, again, these enzymes that these fungi produce through different means such as wheat seed, wood chips, chitin, and keratin. And that's it. So I will stop sharing.